today we are going to be talking about quicksort. This is the second sorting algorithm we are discussing in this series of lectures. The first one was insertion sort, for which we had argued a worst case running time of order n square. So today the quicksort algorithm we are going to look at is also going to have a worst case running time of order n square, but we will argue that on an average in expectation it takes only about n log n time, and it is a quick algorithm. In practice it is very fast with very small constants. The another property of this algorithm is that it is an in place sorting algorithm. What is an in place sorting algorithm? An algorithm is called in place if you do not require any additional memory to do the sorting, right. So, we will assume that the numbers are given in an array, the n numbers are given in an array, we will not need any additional memory, maybe memory for one or two more variables, but we will not need any additional memory to do the sorting. So, that is called an in place sorting, and that is typically a good thing to have, because space is at a premium, especially when you are trying to solve a large collection of numbers. So, this algorithm falls into a paradigm which is called a divide and conquer. Okay, I am not going to be saying too much about this at this point, because we are going to be seeing a lot of divide and conquer algorithms in the course, in this course. At a very high level, the idea behind divide and conquer is the following: that you are given a certain problem that you want to solve, you divide the problem up into two or more pieces, you solve the problem for those smaller pieces. Okay. So, that would be, so the divide step would be, in the case of quicksort, it would be that we will partition our array, we will take the array which stores the n numbers and partition it, break it up into two parts. One is we will call the lower part, the other we will call the higher part. The property of the lower and the higher part would be that every element in the lower part, every number in the lower part would be less than every number in the higher part. Okay. Now, how does this help us if we do such a partition? Well, if I sort the lower part now and I sort the higher part and I put all elements of the lower part first and follow it up with all elements of the higher part, then the entire thing is sorted, right. I have sorted the lower part, I have sorted the higher part, every element here is less than the element in the higher part, yeah. So, the entire thing is sorted. So, that is the combining part, and in this case it is trivial because nothing needs to be done, but quite often in a divide and conquer algorithm you have to do something to do the combine, and we will see examples of this later. So, we will go one step at a time. We will understand first how this partition is done. Okay. So, we will give a algorithm to do the partitioning, which will be a linear time procedure. So, the partitioning is done around what is called a pivot element. Okay. I will take one of these elements as a pivot, and everything which is smaller than the pivot will be my lower half, lower part of the array, and everything which is larger than the pivot will be the larger part. Okay. So, for instance, in this example I am going to, so this is the procedure to do the partitioning. It takes as parameters the array A, and P comma R are the limits of the array, right. So, P here refers to this location and R refers to this location. This could be part of a larger array, yeah. So, this just says that partition the sub array from P to R, okay, and we will see what it will do at the end of the procedure, yeah. So, I am going to take AR would be this element X, I will put it into X, which means X is going to be my pivot element. Okay. So, X would contain 10, and now what is this doing? This is I is getting the value P minus 1. So, I is assigned to something before P. So, this is P and this is R, location, this location is R and this location is P, yeah, and I is getting P minus 1 and J is getting R plus 1. So, which means I and J are just before and after the end, the start and the end of the array, the sub array that we are interested in. And now we are just going to go through this loop while true, which means we just continue going through this loop till we break out of the loop. And what is this doing? This is saying repeat j is j minus 1 until aj is less than or equal to k. So we are looking at this index and we are saying keep decrementing it till I reach a location which is less than or equal to, what was x? The pivot 10. So keep decrementing it. So I decrement j till I reach a location which has content less than or equal to 10. So I already reached such a location. So I stop decrementing. Okay. Now I go to the next loop where I am incrementing I till I reach a location which is greater than or equal to 10. So I already reached a location which is greater than or equal to 10. Okay. Now what am I going to do? Recall that I want everything in the left part to be less than 10 and everything in the right part to be more than 10. So these are in some sense culprits, right, because this is more than 10 and it is in the left part, and this is less than or equal to 10 and it is in the right part. So we will like to swap them, and that is what we will do here. Exchange AI AJ means just swap these contents, right. So I swap these contents. So in blue I will denote everything which is part of the left part, and orange would be everything which is part of the right part. So everything in the left part would be less than or equal to 10, which was my pivot element, and everything in the right part, which is the orange part, will be greater than 10, greater than or equal to 10. Yeah, good. And now we will continue this. So I is, recall I is here at this point and j is here. So once again I am going to keep decrementing j till I find an element which is, what do I have to find? An element which is smaller than 10. So I found one already, and I keep incrementing I till I find an element which is larger than 10. So that actually I will find right here, and once again I will swap these things. Yeah, so I swapped them and I continue with j. So j will keep moving till I find something which is smaller than 10. So actually I found immediately one which is smaller than 10 at this location, and it will keep moving till I find an element which is larger than 10. So this is not larger, so actually I will end up till this location 19, and I will once again swap 8 and 19. Yeah, I swap 8 and 19 and I get this. This is already smaller, so this is also marked blue. This. So now j would continue decrementing till I find something which is smaller than 10. J is searching for something which is smaller than 10. So it will come here. It will come to this position, right? This is the first element which is smaller than 10. So it comes here, and I will continue incrementing till it finds something which is larger than 10. So it comes here, and now I and j have crossed each other. So which means our job is done. Yeah, as you can see. So that's what. If I is less than j, then you do an exchange. If I is more than j, which means they crossed each other, then you exit. Return the procedure, and what are we returning? We are returning the value of j, which tells us what is the boundary of the two halves. So this is my left half. My left half is from P to j, and my right half is from j plus 1 to r, because I am only returning j and not I, right. So j plus 1 to r is my right half. Is everyone okay with this? How much time does this procedure take? Order n. Is this clear that it is taking order n time and no more? Because हम क्या कर रहे हैं? At every step we are decrementing j. So how many times can j be decremented? At most n times the size of the array. Yeah. And how many times can I be incremented? At most the size of the array. So this loop is done at most n times. This loop is done at most n times. And every time we increment or decrement, we might have to do one exchange in the worst case. So this also is never be done more than n times. Right? Questions? Someone is trying to say something. No? Okay. Yeah. So it's a simple way. So why did we do it in this manner? You could also have done it in a slightly different manner, right? After all, we are taking the pivot and we are saying compare every element with the pivot and put everything which is smaller in the first few locations and everything which is larger in the next few locations, right? But if you try to do it some other way, you will require more memory. Yes, right? One way you could do is take one element at a time, put it in some other array, and then copy that array back into this place, right? That would be one way of doing it, but that will take more memory. So we wanted to do it in place, as in keep all the elements in this array, not take any additional memory space. Right? So we can do this partitioning in place, that is no additional memory, and in linear time. Yeah, the best possible.
divide while, that will be taking order n time, right?
Yeah, okay. No, so I am saying let's look at this repeat until loop. Over all the while loops, let me just look at this one statement. Total number of times this is executed. Not in one run of in one iteration of the while loop, but all while loops put together. How many times is this statement executed? At most 10 times, because I can decrement it only at most 10 times.
Sir, it may be possible that we are repeating that particular for each while, right? So isn't it possible that for every while we need to run it for n time?
No, that's not possible. Yeah, because for a certain while, for a certain run of the while loop, for one particular run of the while loop, I might decrement it, let's say 3 times. Then for the next one, I might decrement it another 5 times, and so on and on. But the sum overall will not be more than n, because
The sum should be
at most
the
10.
sum would be less than n.
That's all I'm interested in, right? The total number of times this step is executed, and this step is executed, and this is executed, and this is sort of n. Good. So this is now my complete quicksort algorithm. I did my partitioning, right? So I have to do quicksort on, let's say, this array, right? Array A between limits p and r, right? So when I do the initial call for quicksort, I'll do 1 to length of A, whatever is the length of A, right? So I'm in general, this would be the thing. So p to r. Now I need to do it only if p is less than r. If p equals r, then there is nothing to be done, or if p is more than r, then again it does not make any sense. So if p is less than r, then I do something. What do? I first find the partition of this part, p to r, right? I invoke the previous procedure. A p comma r, what does it do? It rearranges the part of the array between p and r such that everything which is less than the pivot is in the initial part of the subarray, and everything that is more than the pivot is in the later part of the subarray. And what does it return? It returns the demarcating line, so to say, right? So that the lower half is going from p to q, and the upper half or the larger half is going from q plus 1 to r. So now I need to sort the lower half and the upper half separately. So I recursively invoke quicksort on the lower half, which is going from p to q, and on the larger half, which is going from q plus 1 to r.
So what does while true mean?
While true just means just keep doing the while loop forever, right? You are asking about the previous.
So we have to stop with something.
When do you stop? When does this while loop stop? It will never. It stops when you return out of this. It's like an exit out of the while loop, like a break statement. You have to come across break statements, right? So when this condition is met, that I is more than j, then you will come to return j and go out of this entire partition procedure itself, right? So which means you also go out of the while loop.
You said that it is a in-place sorting algorithm,
Yes.
but here we are calling recursive, making recursive calls.
Right.
Won't that cause the space to be piled up? The initial calls will be piled up in the. So would it take space on the?
It will take, okay, so when we call this recursively, yeah, when we call quicksort this recursively, so note that I don't have to copy the array A, right? It's the same array that keeps getting used, yeah. The only thing that would perhaps, we might have to create more copies of the variables. Actually, we would only be creating additional copies of these parameters that we are passing, right? But and that is space that is created on the stack. Okay, so yeah, so we are ignoring this. You are right, but we are not, taking any additional memory for the elements that we have. They are all sitting in a single array.
Sir, in quicksort, isn't the partitioning done about any random number rather than a fixed number?
We are coming to all of that, right? What element should we partition around? What should be our pivot element? We come to that in a minute. But everyone understands quicksort? You took a pivot element, you partitioned the array around that pivot element, and you said, okay, let me sort this left half, let me sort this right half, and then I'm done, right? And how do you solve the left and right half? Repeatedly by the same procedure. right? And since we have a notion of a left half and a right half, therefore we need to write a quicksort procedure in this manner, right? Because this will specify the limits of the subarray that you are sorting, P comma R. Yeah. Okay, good. Okay, so let's now try and analyze how much time does quicksort take. We have only seen that the partition procedure takes order n time, linear time, but we don't know how much time quicksort takes. So the time taken by quicksort will depend upon how the split is happening. What do we mean by that? How many elements end up in the left half and how many elements, I should not say left half, but left part, right? So how many elements end up in the left part and how many elements end up in the right part? Yeah, that's what we should find out, and that will determine how much time quicksort is taking, and let's see why. So if at every point, suppose the following was happening, right, that every point we actually were dividing the array up into two equal halves, yeah, which means I started off with n elements, this here, right, and मैंने इस तरह से pivot pick किया somehow, or lucky I was, or whatever it was, my pivot was such that it was the median, let's say, which means that half the elements were less, half were more, so half elements ended up in the left half and half elements ended up in the right part. Then when I did a quicksort on this, again I was lucky, right, again I picked a pivot such that it divided the thing up into two parts. And when I did my quicksort on this, again I was lucky, it happened that this divided it up into two parts, equal parts, and so on and on. So suppose I was lucky at every step, so then how much time am I taking? Right, let's see, how much time did I take to divide this array up into two parts, n by 2 and n by 2? N time, the size of this array. Yes? We saw the partition procedure took n time, order n time. How much time did I take to divide this array of size n by 2 into two parts, n by 4 and n by 4? N by 2. N by 2 here and n by 2 here, so that it becomes n. Then to divide this up into two parts, n by 8 and n by 8, I again took n by 4 here, n by 4 here, n by 4 here and n by 4 here, so that's also n. So in effect, in each level of this tree that I have drawn in this manner, I am taking order n time, yeah, to do the partition. And how many levels are there in this tree of mine? Log n, because eventually you will end up with 1 and there would be log n such levels, right. So the total time taken is order n log n if I am lucky, but I am not lucky, I am Naveen, right, which means that
Sir.
so
In this, sir, we are using the fact that the partitioning takes big theta of n, sir. So, but we only concluded that it takes big O of n time.
Can you also, so why did I write theta of n and not O of n? Who can tell me? Can you also say that the partition will take at least, or at least omega n time, will take at least n time? Yes? Because when did we say we would stop? When our I and j would interchange? So I has to go at least till some part and j has to go, so the total number of times I will increase I or decrease j is at least n, right? The total number of times I will increase I, I'm not saying that number of times I will increase I is at least half, I'm not n by 2, maybe I increased I only n by 4 times, but then it means I decreased j at least 3n by 4 times. So the sum is at least n. Yeah, so I need at least n times. So which means I need at most n times, I need at least n times. So the exact time is really some constant times n, theta of n, and so I can actually say an equality. Yeah. Good. So what happens in general, right? If you are not lucky, what happens? So what is the worst case? N square, because I right, right. So when we partition, तो एक तरफ एक ही एलिमेंट आता है और दूसरी तरफ सारे एलिमेंट चले जाते हैं बाकी के, right? One side gets one element, the other side gets n minus 1 elements, right? So we could have such a situation, t1 plus tn minus 1. So this is again I am writing a recurrence relation. Time to quicksort n elements equals the time to partition, that was the very first step of our quicksort procedure, plus the second step of the quicksort procedure was quicksort the left part. Let us say the left part has one element in it. So, T1 plus the time to quicksort the right part, which has, let us say, n minus 1 elements, so Tn minus 1. So, this is our recurrence, and let us solve this recurrence in exactly the same manner that we did earlier ki Tn minus 1 mein, right. So, T1 I am assuming is 0. So, this is just Tn minus 1 plus theta of n, right. If you have one element, there is nothing to be done, it is sorted. So, this is just Tn minus 1 plus theta of n. Now, what is Tn minus 1? It is Tn minus 2 plus theta of n minus 2, n minus 1, sorry. So, Tn minus 2 plus theta of n minus 1, and Tn minus 2 is Tn minus 3 plus theta of n minus 2, and so on and on. So, it essentially becomes theta of k, k going from 1 through n. Yeah? Not clear? No? Chaliye, let us make it clear. What is this? Okay. So, what all I am saying here is this is then equal to T of n minus 2 plus theta of n minus 1 plus theta of n, which is T n minus 3 plus theta of n minus 2 plus this term, which is equal to T n minus 4 plus theta of n minus 3 plus this entire thing, and so on and on. So, that is all you will get, right. So, this is what you get, which is basically theta of n squared. Yeah, n squared, k going from 1 through n, sum of k is just n squared, and so you get theta of n squared, right. If this theta is bothering you, just replace it by some constant times n. Okay. Is this clear to everyone? So, this would be the worst case, right. So, the best case is when you do a half and half split, and the worst case is when you know it is a very skewed slip split. So, this is what the worst case looks like pictorially: n divided into 1 in n minus 1, n minus 1 divided into 1 in n minus 2, n minus 2 divided into 1 into n minus 3, and so on and on. And what will be the height of this tree now? N, right. And each step, this you are taking time n, again you are taking time n, n minus 1, n minus 2, and so on, all the way down to 1. So, that makes it n squared. Right. So, when does the worst case appear? So, suppose we were doing the following scheme, right. We were saying, let me take the last element as the pivot always. That is what we did to begin with. Let me take the last element as the pivot, right. So, if my input is sorted already, let us say in increasing order, and I took the last element as the pivot. So, how many elements will be in my lower part? N minus 1 elements in my lower part, and only one element in my upper part, because there is no element larger than the last element, right. And then once again, to sort the lower part, I took the last element as the pivot. So, once again it will get divided in this manner, right. So, the worst case would happen when the input is already sorted in ascending order or in descending order. Even in descending order, you will take n square time. Yes or no? Because when it is in descending order, you took the last element as a pivot, it is the smallest element. So, अब आपका जो left half हो इसमें there will be one element, and right half will have all the n minus 1 elements in it. Yeah, and you will keep doing this, and this is what will happen. Right. Similar kind of a thing happened in insertion sort, if you remember. Insertion sort mein we said the worst case would happen when it is in descending order, right. Because if you recall, in insertion sort, we were taking an element and figuring out the best place to put that element, and we would go from the end to find the best place. So, if it is sorted in decreasing order, then the best place is always the front of the array. So, you will have to go all the way to the front of the array at every step, right. And so, it is again 1 plus 2 plus 3 plus 4 and so on all the way up to n. So, you get the again same n square. But in insertion sort, if the array was sorted in increasing order, then how much time do you take? Then it's the best case, because you don't have to move back anymore, right? It's already, every element is at the right place, so it just takes constant amount of time, right? So that's a comparison with insertion sort. But here, both in whether it's sorted increasing, sorted decreasing, you might end up with something like an n squared time. Yeah. So worst case seems to occur more often here. Let's continue with this analysis, right? So we saw, agar if the split was half and half at every step, then we are lucky, right? And we get n log n time. Now suppose it was not half and half, but it was 1/10, 9/10. That is 10% of the elements end up on one side and 90% of the elements ended. And suppose this was happening at every stage, right? So you will not call this lucky, right? Because it's not half and half, but it's still good, which is what we'll argue now, right? So at the first stage, this is what happens: n by 10 elements on one side and 9n by 10 elements on the other side. How much time did I take to do this partition? N time. Then this n by 10 got divided into 1/10 on one side and 9/10 on the other side. 1/10 means n by 100 on one side, and 9/10 of this is 9n by 100 on the other side. And this 9 by 10n also gets divided into 9n by 10 on one side and 9/10 of this guy, which is 81 by 100 n on this side. How much time did it take to partition this into this and this? N by 10 number of elements, and so for this, so the total time for this is still n. So similarly, the total time for every level will continue to be n, but now how many levels do I have? Let's figure out what the right number. So let's just look at the largest number we have as we go down one level at a time, right? Because the largest number is the one which we want that all the numbers go down to 1. So the largest number is the one which we have to say goes down to a 1, right? So at this root we have n. The largest number at this step will be 9n by 10, because the other number is smaller. Now what will be the largest number at this step now? It will be the 9/10 of this guy, which will be the largest one. So that will be 81 by 100n. The largest at the next step would be the 9/10 of this guy. यहाँ पे जो largest था उसका जो 9/10 fraction है, that will be the largest guy at this step, which will be this, and so on and on. So the largest number at every level is decreasing by a factor of 9 by 10. How many times can it decrease before it gets down to 1? At most log of n now to the base 10 by 9, because it's decrementing by a factor of 9/10 at every step. Yeah. When it was decrementing by a half at every step, we were saying log n base 2. So if you just work out the math, it will be log n to the base 10 by 9, right? Which is order log n. It's just some constant, it's a different constant times log n now. So once again, the height is order log n. And so the total time taken is order n log n, because at each level we are taking a total time of n, and number of levels आपके log n. Yes?
So won't the left be finished before the right?
Yeah, but so what? Even better, right? This is, we are only providing an upper bound. Yeah? Okay, so even if the split was in this strange manner, 1/10 and 9/10, or any constant fraction, there was nothing sacrosanct about 1/10, 9/10. I could have said 1/37 and what? 36 by 37, right? Even that is okay, no problem. Even then we will be able to argue log n. Yes? There is nothing spectacular or special about 1 by 10. Right? The important thing is, we are saying a constant fraction of the numbers go on one side. A constant fraction of the numbers go on one side. We can't afford to say only one number goes on one side. That becomes bad for us. When only one number goes on one side, or only two numbers go on one side, then we will end up taking n square time. But if we say a constant fraction, 1/10 or 100th or 1000th or 1 millionth, the height would still be only log n. Yes? Okay, so we'll do a formal analysis from starting from the next slide, but just to give you a little more motivation on this. So suppose we were to alternate the lucky and unlucky cases. Even then you can prove a log n depth, right? So what was our unlucky case? 1 and n minus 1. And what was the lucky case? N minus 1 divided into 2, n minus 1 by 2 and n minus 1 by 2, right? How many operations did I take here to split? N. And how many operations did I take here to split? N minus 1, right? So in total I took 2n minus 1 operations here, and after 2n minus 1 operations or comparisons, I managed to split it into n minus 1 by 2, n minus 1 by 2 and 1 with 2n minus 1. So now I can again bring the same tree, right? I'll get a recurrence like this. So you don't have to, so I can think of it as this now, that with theta n, or in particular 2n comparisons, I managed to split it into n minus 1 by 2 on one side, and let's say n minus 1 by 2 plus 1 on the other side. Actually I managed to a 3-way split, right, because the 1 is coming here, right. So once again we'll have a depth of only log n, and I took 2n in each step, so it's 2n times log n or some such thing, right. So we'll not worry too much about this. Let's try and prove, let's try and do this formally, right. So it seems that for many scenarios we will get a log n. We want to argue that this really is the case, that the expected time, now I am using the word expected time here, the expected time is n log n. No, not sorry, expected time is, I still need to say a little bit more before I get to expected time. So what is the best thing to do? We want, so we said we will be lucky when we always partition half and half. So the best thing to do would be to find the median element, right, as the pivot. Pick the median element as the pivot, and that will break up my array into 2 equal parts, and that would be great. But how do I find the median element? Huh? Sort the numbers and then find the median element? Yeah, that would be one strategy, except that sorting is what we are trying to do in the first place. Yeah, so finding median element is not straightforward. You will see a procedure for doing it in your next algorithms course.
So we can get somewhat close to the median by dividing the array into some odd number of small arrays, then sorting these, as in like divide the array into small arrays of size 5.
Okay.
And then sort them, then take the median of these. Now repeat this process until you get one number. That will be close to the median, and we will take log n steps.
Right. So you can actually compute a median element in linear time, but it is a fairly involved procedure which you will learn later. For now, what you will do is, since you want to find the median element and you can't find the median element, you will just pick a random element and declare that. Okay. So that will give me, so what we are going to do is we are just going to pick a random element as our pivot. Okay. So we said we don't want to pick a specific element as the pivot. Why? Because if I decide I always want to pick the last element as a pivot, then if my sequence is, let's say, in decreasing order or increasing order, then I am stuck. I will stuck with an n square running time. So I will just pick a random element as the pivot. Okay. So we are going to look at, so this is what we call a randomized algorithm. What's a randomized algorithm? An algorithm which is basically making some kind of random choices, right? And we'll analyze what this algorithm does. We'll analyze the running time of this algorithm in a minute. So this is what randomized quicksort is. So we'll assume all elements are distinct. We partition around a random element. A pivot is a random element, and so, well, the random element, we just pick any element at random, right, with the same probability. So what kind of splits can we get? We can get all kinds of different splits. If I have n elements, I can get a split of 1 and n minus 1. I can get a split of 2 and n minus 2, and so on and on. And what will be the probability of these splits? Will all be equal, right? They will all be with probability 1 over n. You understand why they would all be equal? because it's a random element, each element can be picked with equal probability, right. So, if I have n elements and I pick the 10th smallest element, then I will get a 9 versus n minus 10 split or a 10 versus n minus 10 split, right. But what is the probability of picking the 10th smallest element? It is 1 by n, because I could have picked any element, right. So, I do not know what I am picking. The 10th smallest element is as likely as the 11th smallest element, which is as likely as the 12th smallest element, right. The probability of each one of them is same. We will see more examples of randomization in this course, right, and you will see it is a useful tool for designing algorithms. So, this is what our randomized quicksort is now going to look like. Okay. So, we are only going to modify the partition procedure and call it randomized partition instead, right. So, once again we are trying to partition the array A between P and R, the subarray between locations P and R, and what do? I begin by finding, so what does random P comma R do? Random P comma R generates a random number between P and R. Okay, let us say that number is I. Between P and R means including P and R. Let us say that number is I, and now we are just going to exchange I and the last element. Why am I doing this? Because this partition procedure, if you recall, was taking the last element as a pivot. Now I want to put my pivot at the last location, so I just exchange this. I just exchange the pivot element with the last location, and then I call my partition procedure, the same partition procedure as before. So, this becomes my randomized partition procedure. And what does quicksort do now? Randomized quicksort, it just, instead of calling partition, it calls randomized partition. The rest is the same. Yeah. So, you understand what it is. So, since our choice of pivot is crucial and we do not know really how to choose the pivot, we just pick a random element as the pivot and let.
Even if we partition it around the last element,
yeah.
so it would still be a random choice.
No, it would not be a random choice. Okay, so what is the difference between a random choice here? So, here is a very good question. He says, if I partition it around the last element, why is that not a random choice? That is not a random choice, because if I give you a specific input, which is, let us say, increasing order, then on that input you are going to take n square time, right, if we partition around the last element. Now, in randomized quicksort, we are not partitioning around the last element, we are picking a random element to partition. Now, when I pick a random element to partition, then given the same sorted sequence as input, you are not going to take n square time. In fact, how much time are you going to take? Huh? We do not know how much time we are going to take. Yeah, that is the interesting thing. Why do not we know how much time we are going to take? We do not know what the pivots are going to be, they are randomly selected, right. So, it might happen that today you run the algorithm and it takes some time, and tomorrow you run the same algorithm and it takes a different time. Yeah, yes or no? Because it depends upon what random numbers were selected, and those random numbers selected decide the pivot, and the pivot, as you have seen, is crucial in deciding how much time we are taking, because if that pivot was a nice one which was splitting the things roughly evenly, then it is going to take less time, and if the pivots were turning out to be bad ones, fairly skewed, then they are going to take more time. Yeah. So, we are going to see all of that. So, now, if we do not know how much time the algorithm is going to take, and it is going to take some time today and some time tomorrow, then what do we analyze? What is it that we can say? The average time, right, or expected, what is also called the expected time, right. So, average over what are we doing now? What is the average we are doing over?
Overall possible input, the time taken over all possible inputs.
So, are we averaging over all possible inputs?
All possible
Or over all possible what? Sequence of random numbers generated, right, in some sense. So, the way to think of it is, fix an input, we are not going to change the input, we will run the algorithm today and tomorrow and day after and so on till the end of this course, right, and then we are going to compute the time and take the average, and that will be our expected time for sorting that specific input sequence. Yeah, okay. So let Tn denote the expected number of comparisons required by quicksort, right? Tn, so again, so Tn is a function of n. The time required, the number of comparisons required to sort n numbers will depend upon how many numbers you have, depend upon it. Now let's recall what quicksort does. Quicksort first partitions. If it has to partition n numbers, no matter what the pivot is, it's always going to require the same number of comparisons. It's always going to require no more than n minus 1 comparisons, right? Because you can think of the partition process as every number is compared against the pivot. Yes, every number is compared once against the pivot, and then all those that are less than the pivot are put on one side, all those that are more than the pivot are put on the other side. So we always require n minus 1 comparisons. Every number has to be compared against the pivot, right? Because we otherwise will not be able to decide whether it goes on the left side or the right side. So this is the part which is the partition, right? Now depending upon what the pivot was, if the pivot was the ith smallest element, yes, if the pivot was the ith smallest element, then on one side how many elements am I going to get? I minus 1. Let's say I get I minus 1 on one side and n minus I on the other side, and the ith element is already, let's say I leave it at the right place. Okay. So now I have to quicksort those I minus 1 elements, I have to quicksort those n minus I elements. How much expected time am I taking to quicksort those I minus 1 elements? T of I minus 1. This is the expected time I take to quicksort these, and this is the expected time I take to quicksort the n minus 1 elements. So I will take this much amount of time in all. But what is I here? I is the ith, I was the fact that the pivot was the ith smallest element. That happens with the probability of 1 over n. So I am going to take this much time with the probability of 1 over n. Right? I am going to take this much time with the probability of 1 over n. I am going to take time t 7 minus 1 plus t n minus 7 plus n minus 1 with the probability of 1 over n. I am going to take time t 13 minus 1 plus t n minus 13 plus n minus 1 again with the probability of 1 over n, and so on and on. Right? So the expected time taken is basically then this sum, right? This quantity summed over all choices of, so I have replaced the I by a j here. So the I, this I is the same as this j here, and each one of them is being picked with the probability of 1 over n. Right? This is how you compute expectation. Expectation. So for instance, just to give you an example, those who are forgetting your expectations, I roll a dice. What is the expected value I see? How does one compute this? Each of the outcomes are equally likely. Each occurs with a probability of 1 over 6. So I see 1 with a probability of 1 over 6, 2 with a probability of 1 over 6, 3 with a probability of 1 over 6, all of that. So the expectation is 1 over 6 times 1 plus 1 over 6 times 2 plus 1 over 6 times 3 and so on and on, right? Whatever value that you get, that's the expected value you would see. Yeah? Everyone with me on this? Some doubt? What should I repeat? What did I just say? Anyone? What did I just say? Throw a dice. Right? Throw a dice. So what are the possible values you get? 1, 2, 3, 4, 5, 6. Each appears, it's an unloaded dice, so each appears with the same probability. Yeah? Okay. Now what is the expected value? What is the expected value? So expectation is defined as, so what is the random variable? The random variable is the number that comes. So the random variable is the number on the dice. Right? So this random variable, let's call it x. This random variable takes 6 different values. Each value it takes with the probability of 1 over 6. Yeah? Probability x equals I equals 1 by 6 I between 1 and 6. Okay. Now what is expectation? Expectation, think of the expectation as just the following. You keep throwing this dice and keep recording the outcome. Keep doing this forever, and then just take the average. Yeah. Okay. So how many, suppose you threw this dice 1 billion times, right? Now how many times are you going to see a 1? 1 billion by 6 times, right? This is what probability means, the probability that it is 1 by 6, right? That if you do the experiment sufficiently many times, then this fraction of the times you are going to see this particular outcome. Itne times you see a 1, so itne times your outcome was a 1. If I am looking at the sum of the outcomes, this will be one sum. How many times do you see a 2? How many times do you see a 3? And so on, right? So let me just complete this. Yeah, which is exactly the same as saying 1 by 6 into 1, right? This quantity here, what is this quantity? This is just the probability of the event that xi equals 1. Yeah. So this is 1 by 6, or I could even have written it as probability, the random variable takes the value 1 times this 1, which is the value of the random variable, plus probability 10 by 9 by 6 is the probability that it takes the random variable. 10 by 9 by 6 by 10 by 9 is just the probability that it takes the value 2. So probability x equals 2 into 2 and so on and on. Probability x equals 6 into 6. Yeah. So that's what expectation is. So one way of thinking of expectation is that if a certain random variable is taking a set of discrete values, then you just compute the value of the probability with which it takes the value times the value summed over all the possible choices is the expectation of the random variable. Yes? Okay. So let's revert to our slides. Yeah. So this is going to be taking this value with a probability of 1 over n. Yeah. Right. And so we have done just the probability times the value summed over all possible choices, which is j varying from 1 through n. Right. And I've just done, so again as j varies from 1 through n, this quantity varies from t0 to tn minus 1, and this quantity also varies from n minus 1 to 0 to t0, which means every term t0 through tn minus 1 appears twice. So I can write this part of the sum as this, and this n minus 1 we are summing it n times and then dividing it by n, so it's just plus n minus 1 separate. And this is a recurrence we saw in the last class. Yeah. It was the recurrence for the expected number of comparisons required to insert a randomly chosen permutation of n elements in a binary search tree. There should be a inner binary search tree somewhere here. Yeah. And what did we prove in the last class? We solved this recurrence and we showed the solution is n log n. Hence the expected number of comparisons required by randomized quicksort is n log n. The same recurrence. Yeah, we solved it before, we are just using that fact. Any questions till this point? Yeah, so this is the analysis which we did, and good. So this is the expected number of comparisons required by quicksort. So let's quickly summarize what is the time taken by quicksort. Worst case time we said was n square, best case time was n log a. We didn't prove it formally why it should be n log n and why it can't be less, but intuitively you can understand that the best thing happens when the two are roughly equal, right? And then we argued that it will take n log n, right? And the expected is once again n log n. And this behavior is similar to what we also saw in the last class. Yeah, when I'm trying to insert n elements into a binary search tree, right? What is the worst case time? N square. It happens when my sequence is sorted. What is the best case time? N log n, again there. And that was, if the first element I was inserting was roughly the median, and the second element I was inserting was n by 4, right, and so on and on. And the expected time was n log n. Okay, this is a crucial difference between what we are doing today and what we did in the last class. Okay. Okay, so this is something I've already said, but let's just recap. What we have done today is that the running time of quicksort depends upon the numbers that are getting generated, right? If the same random numbers were generated, right, then the running time would be the same for a given input. Okay. So the same thing I said, I fix an input, the running time could be some value today, it could be some value tomorrow, because the random numbers generated could be different. And what we have done is we have taken expectation over these different random numbers that have been generated by saying that today we will compute what the value is, tomorrow we will compute what the value is, and so on, and take the average. We are essentially, we are doing this for one fixed input. And we said, if I fix an input and I compute this value, it turns out to be n log n, right? That's what we did. And nowhere we use the fact that what the input was, really, come to think of it. No matter what the input is, your expected time is turning out to be n log n. Yes? Yeah? So somehow, this is actually what some of the slides were also saying before. When we said we would take a specific element as the pivot, let's say the last element as the pivot, we saw that the running time would depend upon what input was given to us. If the input was sorted, we would take n square time, but if the input was such that the last element was the median element, then once again we would get this half and half split, and so on and on. So you could, if I had taken a specific element as the pivot always, then my running time would depend upon what the input sequence was, what the input order was. But I got around that somehow, right? I said, let me randomly pick my pivot element, and now what has happened? The running time doesn't really depend upon what my input is. It depends upon what the random number choice is, which in expectation will give me a running time of only n log n.
What specific advantage does it provide? Because whatever we are giving, we are not bothered. When we are making an algorithm, we are not bothered about what inputs are going to be, and all that we don't know what inputs are there to be. So how does this make things better? We don't take any fixed element as a pivot. We don't. The input does not. The algorithm time is independent of the input.
The algorithm time is independent upon the input. How does no? So what we are trying to say here is that when we say it's independent upon the input, we are saying that no matter what input the adversary gives us, right? You are trying to maybe beat my algorithm. You want my algorithm to take as much time as possible. So the point here is that you cannot come up with any such sequence, right? No matter what sequence you come up, what sequence of numbers you come up, my algorithm will take a time which in expectation is n log n, which quite often will turn out to be n log n.
But in practice, what we are going to do, we are making an algorithm to work somewhere.
Yeah.
So there nobody is going to beat our algorithm. We have to make an algorithm that works well.
Right.
So there may be a case कि one particular kind of inputs may be more probable.
Right.
So, but if we look at from this point of view that we want to make it independent of the input,
right,
then this kind we are making it random. So it may turn out that if for that kind of inputs.
Right. So if we knew what kind of inputs we were getting, then perhaps it makes sense to design the algorithm for those kind of inputs. Right. But this is not what we are doing here, because we are not designing the algorithm for a specific input sequence or specific kinds of inputs. We are saying we want to be able to consider all possible inputs, and in doing that we want an algorithm which really does not depend upon what the input is. Its behavior is independent of that. Okay. Now what did we do in the last class for binary search tree? And I want to make this difference very clear, and this is the last slide, so just listen carefully on this one. For the binary search tree, we were doing an average over what? So we said take a particular input sequence and it is going to take a specific amount of time. Whether you run it today or you run it tomorrow, it's going to take the same amount of time. That was not a randomized algorithm. It was a very specific algorithm. There were no random choices being made. It would take the same amount of time no matter when you run it. But if I took a different input sequence, it would take a different amount of time. And if I took a third input sequence, it would take a third different amount of time, and so on and on. And there what we were doing was, we said let's take the average over all input sequences, over all possible n factorial different permutations. Right? We took the average over all of them and then we got n log n. Right? You understand the difference? The recurrence is the same, but there is a vast difference between these two things that we have done. One was what we call an average case analysis. Right? We looked at all possible inputs that can be there of numbers 1 through n. There are n factorial different permutations, so there are n factorial different inputs possible. We looked at all of them, we computed the time taken by the algorithm for each one of those inputs and took the average. Right? Today on the other hand, ours was a randomized algorithm. Our algorithm was taking different times depending upon what the random numbers were. And today we were taking the average over the random numbers that were getting generated and not over the inputs. The input was fixed. Okay? So with that I am going to end today's lecture. So we saw quicksort and we did the expected time analysis for randomized quicksort.